All right, thank you very much. Thanks a lot for the invitation to participate at Early Universe from Home. It's really a pleasure to take part this year. So the organizers asked me to give a pedagogical introduction to cosmological correlators, which I'm very happy to do. So let me get started by just reminding you that correlation functions are the main observables in cosmology. We measure them at different times in the history of the universe. So at very early times, we see 2-point correlations in the cosmic microwave background. At late times, we see 2-point correlations in the distribution of matter, for example, the galaxy power spectrum. And so by measuring them, we can learn both about the composition of the universe and its initial conditions. So you have initial fluctuations defined at very early times via transfer functions. These are related to late time observables. And these transfer functions depend on the cosmological model. They depend on cosmological parameters. So by measuring late time correlations, we learn both about the composition of the universe and its initial conditions. Of course, doing so has led to a number of very important surprises. So we have learned that the universe is filled with dark matter and dark energy. We don't know exactly what these components are. And we have learned that explaining the initial conditions requires a period of evolution before the hot Big Bang, most likely a period of inflationary expansion. So in recent years in particular, there has been enormous progress, I would say, in understanding the theoretical structure of these objects. So inspired by the fundamental importance of cosmological correlators, there has been a large community of, as you can see in this image here, mostly junior contributors who have made enormous progress, I think, in understanding at a very theoretical level the initial conditions of our universe and theoretical structures that can arise in these initial conditions. So this here is a picture of a workshop that we had a few months ago in Taiwan, where we had about 80 people kind of discussing these type of things. So unfortunately, in this talk, I will not be able to review this in any detail. Luckily, Enrico Payer has given a fantastic review just a few weeks ago at the QCD Meets Gravity conference. And so that talk is available on YouTube. So I encourage you to have a look at that if you want to get a more comprehensive view of the subject. Now, besides kind of theoretical developments, observations are continuing to improve. And so, in fact, we are reaching an interesting point in history, I would say, where large-scale structure observations will, for the first time, measure more modes than the CMB. And so if we learn how to access information from those modes, in principle, future observations of galaxy surveys like SPHERICS and Euclid and DESI will be able to surpass the CMB in terms of raw constraining power. So then it becomes interesting to ask what type of lessons we can learn about both the late time universe and its initial conditions from those observations. All right, so this brings me to the outline of my talk. So there's roughly going to be 3 parts. I first want to say a few more things about the observed correlations in the late universe. I'm basically just going to flash for you different types of correlators that we have observed and what type of information is encoded in them. I'll then focus mostly on describing the initial conditions for these correlations and what we've learned about these initial conditions. And then finally, I'll describe kind of these more recent developments on trying to constrain the initial correlations on the basis of physical consistency, so which goes by the slogan of the cosmological bootstrap. So I need to apologize. This is going to be a rather wild mix of material. Unfortunately, I didn't have time to kind of make a very polished and comprehensive review of the subject, and so I've mostly just kind of collected things that had lying around, and hopefully I can kind of put them together in a somewhat coherent fashion for you. Okay, so let me get started by saying a bit more about observed correlations. So of course, as you all know, the most important correlation function we have ever observed is the 2-point correlation function in the cosmic microwave background. So I've indicated here, so here this is the power spectrum of CMB anisotropies, this famous plot by the Planck collaboration. And so here I've indicated a number of physical characteristics of our universe that are encoded in this very specific shape of the power spectrum. So you see that there's these acoustic oscillation features in the CMB power spectrum. The position of the first peak tells you about the overall geometry of the universe. It's an indication of the presence of dark energy in the universe. The height of the peak depends on the relative amount of matter and radiation in the universe. And since we have measured the radiation density from the temperature of the CMB, this then tells us about the amount of dark matter in the universe. The ratio of odd and even peaks depends on the amount of baryons in the universe. And so we get an independent measurement of the baryon density. We can compare that measurement to BBN and get consistency between those two different measurements of the baryon density. And then the damping of the CMB power spectrum depends on the density of neutrinos in the universe. And so we have an independent confirmation that there are 3 neutrino species as predicted by the standard model of particle physics. Now, the presence of these CMB anisotropies, of course, arises from density fluctuations in the early universe. When photons scatter off free electrons at the moment of last scattering, this is predicted to also produce CMB polarization in a way that's correlated with the CMB temperature fluctuations because the mechanism is that of scattering off these density fluctuations. And so that's predicted and has now also been observed, of course, by WMAP and then also by Planck. And so in fact, what you're seeing in these figures here is not a fit to the polarization power spectra and the cross correlation of temperature and polarization, but it's an actual prediction. So given the TT power spectrum, you can predict what you're expected to see in EE and in TE. And so these gray curves that are shown here are predictions made on the basis of the TT spectrum. And then there's just the data points that are overlaid on these predictions. So it shows a remarkable consistency of our understanding of CMB fluctuations and the way that CMB polarization is generated. Now, when we observe the CMB, we of course observe it, after it has traveled billions of years through the universe and reached us. The CMB photons are being deflected by the large-scale structure of the universe, so we see a lensed version of the CMB. And so we can measure the lensing potential that's created by the intervening large-scale structure. And so here's a 2-point correlation function of that lensing potential. And so it probes, it's mostly generated by structures living at a redshift of about 2. And so it mostly probes the late time expansion and geometry of the universe, as well as the growth of structure. And so we have an independent test in the way the kind of structures grow at late times and how things are related to the initial conditions. Now, another late time observable is, of course, the distribution of galaxies themselves. So gravitational clustering produces this distribution of galaxies. And so here's the power spectrum that you derive from this measured distribution. It has a very characteristic shape. The peak of that power spectrum tells you about the relative amount of matter to radiation again. In fact, it's related to the scale of matter radiation equality. So by measuring the position of this peak in the spectrum, you get another measurement of the matter density of the universe. On short scales or large wave numbers, there's a suppression of power coming from neutrino masses. And so recently, in fact, they were the first very interesting constraint on neutrino masses coming from this small scale region of the matter power spectrum. Another interesting probe is so-called baryon acoustic oscillation spectrum. So we have already seen oscillations in the CMB. Those are generated by oscillations in the photon baryon plasma before the time of recombination. That same physics is also imprinted or later gets transferred into the dark matter power spectrum, and then the clustering of galaxies, which is dictated by the location of dark matter. And so here, what you're seeing is both in Fourier space and in real space, the two-point correlation function when zooming in into this baryon acoustic oscillation feature. So it gives you a measurement of the projected sound horizon at late times. So it constrains the geometry of the universe, and it helps to break degeneracies that exist in the CMB only measurements of the fluctuations. There's also a subtle effect that's created by the presence of free streaming neutrinos. And so here I refer you to work by Benjamin Balish, who has analyzed in great detail features that neutrinos leave on the temporal phases of these baryon acoustic oscillations. And so this is something you can see both in the CMB and also in the large-scale structure. All right, this was just a very quick run through to some of the most important cosmological correlators. It's rather remarkable that all of these measurements are fit by a simple 6-parameter model, a model that involves dark energy, dark matter, baryons, and an optical depth to reionization, and then 2 parameters, AS and NS, for the initial conditions. So it's an extremely simple model, I would say, lambda CDM, but it's also a strange theory because arguably none of these 6 parameters here is understood from first principles. Yeah, so we don't know what dark matter and dark energy are. We don't know what created the baryon asymmetry of the universe. We are still uncertain about the details of reionization, and therefore the value of the optical depth is not a parameter that we predict from first principles. And then we also don't know in detail what created the initial conditions, whether it was inflation or something else. And if it was inflation, how did inflation occur? What mechanism was responsible for it, and so forth. So in fact, it's this last aspect of the initial conditions that I will focus on for the majority of my talk today. All right, let me so therefore move on to describing what we have learned about the initial conditions of our universe from observations. So first of all, let me highlight that on the relatively mild assumption, we can take the observed correlations like the ones that I've shown you just now, and we can trace them back in time to primordial correlations that live on the reheating surface. So the initial surface of the hot Big Bang or the end of inflation. And we have learned a few interesting facts about initial conditions when we made this transfer from late time fluctuations to the primordial fluctuations on the reheating surface. So let me just mention 4 important facts that I believe we have learned from observations about our initial conditions. So first of all, we have learned that the fluctuations span apparently super horizon scales at the time of photon decoupling. So there's correlated structures on scales that are larger than the naive distance of the sound horizon at, or the particle horizon at recombination. So in the standard hot Big Bang scenario, they will be out of causal contact. And so it's totally impossible for these structures to be correlated over such large distances. So this means they must have been created before the hot Big Bang. I think this is an amazing fact that 30 years ago or before WMAP, I would say, we didn't know for certain that this was the case. There were theories that of course suggested something like this, like the theory of inflation. But this is really now an observational fact that the universe began before the hot Big Bang. There was some earlier high energy period that created the initial fluctuations. So the question then becomes, what exactly happened before the hot Big Bang? What physics created these initial conditions? And so the second clue that we have is that the primordial fluctuations are observed to be nearly scale invariant. So we can take this featured spectrum in the CMB, trace it back to early times on the reheating surface, and we find something that has equal power on all scales. And so this is a natural prediction now of the inflationary expansion of the early universe. So of course, during inflation, as you all know, space expanded exponentially. So very short distance microscopic quantum mechanical fluctuations got stretched to macroscopic scales. This work was worked out by many people in the 80s. And then the predicted correlations are scale invariant because the inflationary dynamics is approximately time translation invariance, meaning that the physical conditions during inflation change very little. The energy density was nearly constant. So then when different modes exit the horizons at different times, they experience approximately the same conditions. And so the same amplitude of quantum mechanical fluctuations gets frozen in at the moment of horizon crossing. And so early structures produce large-scale features, and late fluctuations produce small-scale features, but with nearly the same amplitude because the physics during inflation is very nearly time translation invariant. In fact, this feature that evolution in time becomes, during inflation becomes evolution in scale on the surface at the end of inflation is going to be very important for us when we talk about the cosmological bootstrap. Yeah. So there's a very interesting correspondence between momentum or spatial dependence on a slice at the end of inflation and dynamical information in the bulk of the space-time during inflation. Okay, we will get back to this in the last part of my talk. Now, a third feature of the initial conditions that we have learned from recent observations is that the primordial fluctuations are very nearly adiabatic, meaning, or exactly adiabatic as far as we can tell, meaning that there's no relative fluctuations in the composition of the universe. So the fluctuations in photons, baryons, and dark matter are somehow synchronized. So all the fluctuations are sourced by a single scalar mode, which we often take to be the primordial curvature perturbation. So how you characterize the scalar mode is gauge dependent. We can often, for adiabatic fluctuations, in fact, you can choose a gauge where there's no fluctuations in the density, and all the fluctuations are captured by a metric degree of freedom, which is the co-moving curvature perturbation. This is only possible if the fluctuations are adiabatic, that you can actually remove all the density fluctuations and put them all into a metric fluctuation. And so this is typically what we then assume, that there's a single scalar degree of freedom, the curvature perturbation zeta, or the Newtonian potential phi, or something like that, that then describes or sets the initial conditions for all the matter fluctuations in the late universe. Right? And of course, the initial conditions could in principle also contain tensor fluctuations. In fact, to some degree, they have to have, because quantum mechanically, the space-time metric will also get excited and produce zero-point fluctuations that then produce a power spectrum of gravitational waves, but we haven't seen them yet, okay? Of course, since this is such a clean prediction of the initial conditions, the search for these primordial tensor modes is one of the primary targets of future CMB experiments. I think the current constraints are something like, the amplitude of the power spectrum of tensors has to be less than 3% of the amplitude of the scalar part of the initial conditions. Of course, this famously produces a swirl type pattern in CMB polarization called the B mode. And so here on the left, you're seeing what this pattern would look like if you ever were to see tensor modes imprinted into the CMB fluctuations. So then the final fact about the initial conditions that I'd like to mention is that the initial conditions are very highly Gaussian. In fact, the size of the 3-point correlations in this scalar fluctuation zeta, when normalized relative to the power spectrum of zeta, is less than 0.1%. So in that sense, the universe is said to be more Gaussian than it's flat. We have measured the curvature parameter in our cosmological model at an accuracy of about the percent level. And so this is an order of magnitude more accurately Gaussian than the universe is spatially flat, okay? And so this Gaussianity is also a very natural prediction of the inflationary scenario. So free fields during inflation would experience Gaussian quantum fluctuations. The initial, the wave function of the universe will be very nearly Gaussian. And so everything is described then by just 2-point correlation functions. However, a lot of the physics of inflation is also encoded in possible small deviations from this Gaussian prediction. So these non-Gaussian correlations, although they haven't been seen yet, nevertheless remain a very interesting probe of the physics of the early universe. In particular, what's interesting about non-Gaussian correlations compared to the Gaussian correlations is that they depend now on more than just 2 points in the sky. And for scale invariant fluctuations, in fact, those 2-point correlations are dictated by just an amplitude. So it's a relatively boring, very featureless correlation function that just depends on a single parameter, or maybe also kind of a tilt to the spectrum. So 2 parameters. While non-Gaussian correlations, 3-point functions, 4-point functions, and so on, a whole function's worth of information. So there's a lot of detailed dynamical physical information that can be encoded in these higher point correlation functions. So in particular here, I've shown you 2 shapes of non-Gaussianity, the so-called equilateral shape that has most of its weight for equilateral triangles in the bispectrum. And in squeezed configurations, it has less signal. And the so-called local shape, where most of the signal, in fact, resides in squeezed triangle configurations. And less support of the signal is for equilateral or flattened triangles. And I've also shown you the Planck constraints on these two parameters. Okay. So equilateral non-Gaussianity is mostly generated by higher derivative interactions of the scalar initial conditions. There's an effective field theory for those scalar fluctuations using ideas from spontaneous symmetry breaking. And then also a couple of years ago, we suggested that there's in fact an important target for the amplitude of those equilateral signals of FNL equals 1. So at the moment, FNL is constrained to be at a level of about 50-ish, so between 10 and 100. And so if observations increase in sensitivity by an order of magnitude or 2, one would be able to test this threshold value of FNL equals 1. And that would then allow you to distinguish between slow roll inflation with small higher derivative perturbative corrections to it, and a theory where these higher derivative interactions are really driving the inflationary dynamics. The sound speed of the fluctuations deviates significantly from 1 and so forth. Those are 2 very distinctive and different kind of scenarios for the dynamics during inflation, and you would be able to start distinguishing them if you could reach levels of sensitivity that probe FNL order 1. Then the second important type of non-Gaussianity is the so-called local type. This is generated by new massive particles during inflation, like in this cosmological collider scenario. And in fact, in the last part of my talk, I'm going to be describing in a bit more detail how we make predictions for this type of cosmological collider. But let me maybe take a break here, and I will return to you in a moment. All right, so let me continue. So far we have mostly talked about observable aspects of cosmological correlators. So I've described some of the key correlators that have been measured in the late universe, and then what kind of lessons they taught us about cosmological initial conditions. And then we ended with this fact that although the fluctuations are highly Gaussian, and so purely described by 2-point correlations, there's in principle, very crucial information that's being encoded in higher point correlations. So it remains very important to understand the kind of theoretical origin of possible higher order correlations. So then in the last part, I want to switch to a slightly more theoretical topic, which tries to characterize those higher point correlations in a kind of new way by asking what's the space of possible correlations that can arise from consistent physical processes in the pre-Big Bang history, and then get imprinted into a spatial surface at the end of whatever happened before the hot Big Bang, which then become the initial conditions for the hot Big Bang evolution. So first, let me state that the challenge, so the challenge in computing cosmological correlators is that in cosmology, energy is not conserved. And because energy is not conserved, the computation of cosmological correlators involves complicated time integrals. So for example, in this picture that I've drawn here, which is kind of the standard cosmological collider process, where a particle is spontaneously produced out of the vacuum. If it's a massive particle, it will then also quickly decay into lighter particles that then get imprinted on the reheating surface. And so these decays can happen at different times. And in fact, the probability for the entire process is the sum over histories of all possible decay events. And this involves then complicated time integrals from -infinity, this is conformal time, at early times, to 0, which is the moment in time when these spatial correlations are imprinted on the reheating surface. And so, of course, such time integrals also exist in the case of scattering amplitudes. In that case, one integrates from -infinity in the far past to +infinity in the far future. But in that case, energy is conserved. So these time integrals become trivial. They just enforce energy conservation at every interaction vertex and become part of the Feynman rules. For cosmological correlators, these time integrals are non-trivial and in fact one of the key challenges in computing these correlation functions. Now, it's another fact, however, that all of this complicated bulk physics is not directly observable. So nobody actually sees, directly into this period before the hot Big Bang. All we can observe is kind of static correlations that are imprinted on this surface. And so this suggests that there should be a more on-shell way focusing directly on these observable fluctuations on this initial boundary that dispenses with the need for computing complicated integrals. And so that's what the cosmological bootstrap is trying to achieve. The key idea of the bootstrap is the following. So instead of following fluctuations through time explicitly, one asks the broader question, what's the possible space of solutions that you can get at the final output of this process that's consistent with basic physical principles? And so it's rather conservative in the sense that we don't look at specific models of the pre-Big Bang universe, but like we try to summarize the space of possible predictions on the basis of an assumption about kind of the basic physical laws that would govern such an evolution at early times. So in particular, of course, these physical principles are easy to describe from the bulk point of view. So we assume the bulk evolution to be local, so all interactions happen locally at space-time points. We assume it to be causal, that we know exactly what causal relationships between different separated points in space-time mean. And we assume the evolution to be unitary in terms of the usual notion of unitarity in quantum mechanics. And then sometimes we assume extra symmetries that evolution obeys. So it's very clear from the point of view of the bulk what we mean by these principles. Until recently, it was less clear how all of these principles are encoded in the final observables, namely the correlation functions living on these spatial slices. And so one of the big achievements, I think, in the last couple of years was that we now have a much better understanding of how each of those principles is reflected in special characteristics of correlation functions living on a spatial slice. So in particular, there's going to be two important characteristics that I want to highlight. So first of all, the allowed deformations of correlation function, meaning that if I'm changing the relative arrangement of points on the spatial surface, the signal will change. And so that change in the signal will satisfy interesting differential equations. So consistency of local and unitary causal evolution in the bulk spacetime will be reflected in differential equations that are formulated purely in terms of the kinematic variables, like the energies and the momenta of the fluctuations on this final slice. And then locality of the bulk spacetime gets reflected in a certain set of physical singularities that these correlation functions will have to satisfy. There's an interesting analytic structure of these correlation functions that we now understand quite well. And then in combination, using knowledge of the singularities plus the knowledge of how deformations of the correlation functions are related to each other, it's possible to reconstruct in ways that are simpler than computing explicit time integrals the final predictions for various processes that could occur before the hot Big Bang. All right, so with that preamble, let me start by first reminding you of the basic kinematics of correlation functions. So in cosmology, we like to describe fluctuations in Fourier space, just because at linear order, different Fourier modes are decoupled from each other. So we then translate correlation functions between, spatially separated points in the real space to correlations between Fourier wave vectors. And so I'm often also going to call these wave vectors momenta, in analogy with kind of the momenta of particles interacting in a scattering process. Because of spatial translation invariance, the sum of all the spatial momenta has to add up to 0. And so therefore, these correlators in Fourier space will describe configurations as closed polygons. So for example, a 3-point function becomes a triangle, a 4-point function becomes a quadrilateral in terms of where each of the side lengths of these objects is described by a Fourier momentum. In fact, the vector is the Fourier momentum, and then the length of the vector we're just going to call energies. Although there's no dispersion relation that relates energies and momenta in the same way that it would in a Lorentz invariant theory in flat space. So now then the question becomes, how does the strength of the correlation change when we change these, the shape of these polygons, when we change their energies, the energies of the external particles? Okay. So the first important fact is that every correlator has a very characteristic singularity when the total energy of a process vanishes. So to illustrate what I mean by total energy, let's go back to a Borg-Feynman diagram for, say, a 4-point contact interaction. So there's 4 lines going out to the boundary. Those are the 4 external fields. Or each of the fields carries a 3 momentum, Ki, K1, K2, K3, and K4. The magnitude of those momentum vectors is an energy, E1, E2, E3, E4. Or here I've written it as magnitude K1, K2, K3, K4. And the sum of all the energies is the total energy of the process. Geometrically, this corresponds to the perimeter of this quadrilateral. Yeah? Each side length is an energy. The sides have to add up to a closed quadrilateral. And so the perimeter of that quadrilateral is just the total energy of the process. And so now I want to take the limit where the total energy, or the sum of all the side lengths here, the perimeter of this quadrilateral, goes to 0. And I want to do this in a non-trivial way. So of course, the trivial limit would just be where each of the individual energies goes to 0. Then all of the modes would just be infinite. It's just a pure gauge mode where all of the wavelengths are infinite wavelength. This is not what we're interested in. What we're interested in is, in fact, an analytic continuation where some of the energies here are taken to be negative. So in cosmology, this never happens, of course, because all the particles are ingoing, and then in the Wunsch-Davis vacuum, all ingoing particles have positive energy. So this is not actually a kinematic configuration that one can measure in the sky. But nevertheless, you can contemplate this limit as an analytic continuation. And as we will see, this particular kinematic limit then carries crucial information about the structure of the correlation function that translates even into the region in kinematic space that we can measure. Okay. So taking this energy E going to 0 then creates a pole in the correlation function. The order of this pole is model dependent. It depends on the number of derivatives carried by the bulk interaction. And the residual of the pole, the strength of the pole, is just the corresponding flat space amplitude. Okay. The reason why all of this is happening, in fact, is easy to understand from the Borg time integral representation. So imagine I take this 4-point contact interaction. In the limit E going to 0, this integration here will be dominated at early times. At early times and finite energy, it would have a highly oscillating factor that kills the contribution from early times. But now when I'm taking energy going to 0, this oscillating factor here disappears, and we're just integrating over an infinite amount of time and get some divergent contribution from this long time integration. Okay. And so that's why we get this energy singularity. For an amplitude, one would get very similar integrations, but now we would integrate from -infinity to +infinity. You would get from this exponential factor here an energy conserving delta function. So there's a one-to-one correspondence between the energy conserving delta functions for an amplitude and then the energy poles that one gets for cosmological correlators because energy is not conserved. Okay, there's a very direct link between these concepts. Okay. Now for contact interactions, this would be the only type of singularity that a correlator has. Yeah. But for exchange interactions, where we have, for example, two 3-point vertices that interact via the exchange of a massive particle, this is precisely the diagram that we're interested in when we talk about cosmological collider signals. In that case, you can have additional singularities when partial energies, meaning the sum of the energies entering each of these vertices adds up to 0. Okay. Geometrically, this corresponds to the sum of the side lengths of a sub-polygon of these larger polygons. So for example, in the case of this quadrilateral here, the quadrilateral can be divided into 2 triangles. The perimeter of the left triangle here is just the total energy entering the left vertex in terms of this bulk picture. And the perimeter of the triangle here on the right would just correspond to the total energy of all the lines entering the right vertex. Okay. So let's look, for example, first at the limit where the sum of the side lengths of this left triangle, or the sum of the energy entering the left vertex, is taken to 0. In that case, the correlation function factorizes. So it has a pole at E left going to 0. On the pole, it factorizes into a 3-point amplitude on the left and a 3-point correlator on the right. Okay. There's a 3-point amplitude on the left because precisely we're getting the singularity from taking this left vertex and effectively dragging it to -infinity because the integration over this time vertex is dominated by very early times. Okay. And so the fact that the correlator factorizes in this particular way can also be understood very nicely from properties of unitarity cuts in the bulk spacetime. And so this was understood very nicely by Harry and friends. All right, so the upshots of this discussion is that we understand extremely well all singular points of correlation functions. And in fact, all singularities of the correlation function are fixed by much simpler objects. In particular, they're basically just fixed by amplitudes, and we know how to compute these amplitudes or parameterize amplitudes for various theories. In particular, these can even be non-Lorentz invariant amplitudes that would then capture some features of symmetry breaking. Okay. So then the challenge to determine the full correlation function is to find a way of connecting these singular limits of the correlation function. In particular, this is necessary because, as I said before, we can't actually measure these singular configurations. And so we need to kind of use these singular configurations as input, but then find a way of connecting them into a larger object that's the full correlation function that's valid at arbitrary kinematics. And then we can go to the see what kind of reflections those singular behaviors have in the physical kinematics that we can measure in the sky. Okay. So there's various ways of doing this. I'll just describe one possibility for doing so, which is to exploit the symmetries of the bulk spacetime to find a differential equation that connects these singular points. So one important fact of just cosmological evolution in general is that the isometries of the cosmological bulk spacetime get translated into symmetry on the spatial slices that create boundaries for the spacetime. Yeah? So this is very manifest in an inflationary context where there's a future boundary to the spacetime at conformal time equals to 0. And the isometries of the approximate de Sitter spacetime during inflation become conformal symmetries on the boundary of the space. Okay? So conformal symmetries are a combination of scaling symmetries and special conformal symmetries that involve also inversion of the spatial coordinates. Okay. So we'd like to exploit this feature that the symmetries of a quasi-de Sitter spacetime become conformal symmetries on the spatial slices that we observe. In quantum field theory, that fact translates into a differential equation in momentum space or in energy space. Yeah, these are so-called Ward identities. And so here I've shown you a specific form of that Ward identity for the case of a 4-point exchange process. Yeah, And so the details of this equation aren't so important. Let me just highlight a couple of non-trivial features. So first of all, there's a differential operator here on the left in terms of, for example, this is written now in terms of the sum of the energies of two of the side lengths of a quadrilateral. And I've called that E1. It's a second order differential operator that when acted on the correlation function produces a source function here on the right with fewer singularities than the full object. So the full object has three singularities: the total energy, the left energy singularity, and the right energy singularity. This differential operator annihilates the partial energy singularities and leaves an object that has only a total energy singularity. So that's a contact interaction, while the thing on the left includes exchange pieces. The coefficients of this differential operator have zeros precisely at the points where partial energies vanish. Okay, so it knows about the partial energy singularities of the correlator. And then here the source on the right-hand side knows about the total energy singularity. So all the singularities of the correlators are kind of encoded in this differential equation. And then by solving the differential equation, one can in fact connect those singular limits. So the idea is you impose these singularities as an input, as a boundary condition for this differential equation. You then solve that differential equation, and the solution is going to be valid throughout the entire kinematic space. But it's highly dictated by, first of all, the functional form of the equation and its boundary conditions, which are the singularities that I described earlier. Okay. Actually, I won't write the solution explicitly. It can, of course, can be done. There's usually two pieces, kind of a power law piece that describes kind of bulk contact interactions, and then exchange pieces in terms of hypergeometric functions. It's not very elucidating to actually write that solution. What I want to do instead is I just want to give you a picture of some of the main physical features that the solution has for physical kinematics and things that you can then actually go out and measure. So in particular, if the theory contains massive particles in its spectrum, then that will be encoded in terms of the amplitudes that we're putting in these singular points of the correlation function. And solving the differential equation then produces a very characteristic feature in the correlation function, namely oscillations as a function of momentum. So what I'm showing here is a slice through momentum space. In particular, on the right here, I'm taking a correlator of 4 points with nearly equal side lengths, so an equilateral configuration. And then I'm going to go, as I'm moving to the left, I'm going to squeeze the diagonal momentum of this 4-point function. At first, the signal will change smoothly as I'm compressing this diagonal further and further. And then at some point, the signal will start oscillating with a frequency that's dictated by the massive particle that's part of the spectrum. Okay? This is the analog of a resonance in an ordinary collider experiment. So in a collider experiment, one starts at low energies here on the left, increases the center of mass energy of the collider. At first, one just traces out the contact interactions of the effective theory. One doesn't have enough energy to produce new particles as a resonance. But then when the energy becomes high enough, there's this resonance peak because now massive particles can be kind of excited and they produce this extra resonant feature. In cosmology, the analog feature is what I described here on the left. So it's also easy to understand that this oscillating feature in momentum space is really a reflection of time evolution of massive particles during inflation. I mentioned before that there's this interesting link between dynamics in the bulk and spatial scale dependence on the boundary. So a massive particle has a wave function that has an exponent, complex exponential piece like this. So there's a oscillating phase that depends on the mass of the particle. And then we are correlating this massive particles at spatially separated points in space. There will be an interference effect that creates then oscillations in the final output correlations. And it's precisely those oscillations that we just predicted using this formalism. And it's important to highlight that what we did is we solved a static differential equation purely in terms of energy variables on the boundary. But we automatically inherit this kind of very clearly time-dependent signature of an oscillation in the signal. All right. So in fact, this is a huge topic. I could have said much more things. I really encourage you to look at Enrico's talk that has many more aspects of this kind of philosophy of trying to reconstruct cosmological correlations on the basis of physical principles. We have a Q&A session, in fact, one of these evenings. And so any questions that you might have on this, I'm also happy to discuss them. All right, so let me just conclude. So I'd like to just highlight that cosmological correlators are a very active area of current research. To me, it's fascinating because it combines kind of very fundamental theory with also experiment and observations. Observations are continuing to improve, and we will be able to have like much more data that describes the initial conditions for our universe that we then need to analyze. And so in the last part, I described that these correlation functions have a rich structure. Much of this structure is controlled by singularities. And there's an interesting flow implied by bulk dynamics in the boundary kinematic space that relates dependence on momenta of these spatial correlations to kind of physical processes happening in the period before the Big Bang. All right, with that, I want to end. Thank you very much for your attention, and I look forward to seeing you in the Q&A. Bye-bye.